So thank you. Can you hear me? Is it okay? Yeah. So I'm going to talk about arithmetic circuits, and it was mentioned before, but I'm going to define it formally anyway. So an arithmetic circuit is a directed acyclic graph from the inputs to the output, and discuss such circuits. The natural operations in arithmetics are addition and multiplication. Also, a more general framework, when we talk about arithmetic circuits, there is always a field in the background. As you can see, this is small f over here. And if you can think about a finite field or a field of rationals, it doesn't matter depending on the application. So the graph may also contain constants from the field. So in this model, as you can guess, the computation is done very, very simple. You start at the bottom and you apply the operation until you reach the top, and this is the output of the circuit. One particular important quantity associated with the circuits and everywhere else is the size of the circuit, which is the number of gates. Intuitively, this represents the amount of resources we need to evaluate the circuit on a given point. So the model of arithmetic circuits, beside what we saw earlier today, this is a standard model for polynomial computation. And in fact, we can phrase many, many interesting problems in this terminology. For example, instead of asking what's the fastest way to compute FFT, you can ask what's the smallest circuit that does so. Likewise, instead of asking what's the best way to compute a product of two n by n matrices, which is an interesting question, you can ask what's the smallest circuit to compute the product. So we're talking about learning here, and the way we talk about learning is through a exact learning framework, which is the exact one of the models to discuss. In this model, we have a learner, a teacher, and a hidden function that the learner is trying to learn, the hidden function f. And to do the learning can ask two types of queries. One type is the what's called membership query. This is simply evaluation. So learner can choose points and ask what's the value on the point A, what's the value on the point B, etc., etc. The other type of query, what's called a equivalence query. In this case, a learner proposes a hypothesis and asks, does the hypothesis represent the function? And there will be two outcomes, consequences. If the answer is yes, then everybody is happy, the job is done. Otherwise, the learner gets a counterexample to the hypothesis. And with this terminology, we have this definition. What does it mean to be exactly learnable? So a class of function is exactly learnable if there exists a learning algorithm that for each function in the class, in time, polynomial in n, the number of variables, and the representation size of f, it can output a hypothesis, describe the function using membership and equivalence queries. So that's the definition of exact learning. So there are obviously other models of learning. Some of them are going to see today, like the PAC model. We have a huge session, so I'm not going to discuss it now. But here is an interesting fact. For arithmetic circuits, it turns out that PAC and exact learning are essentially equivalent. So this is why we're not considering PAC learning, which is sometimes more natural. So back to learning, if we look at the learning literature, we have a vast literature, a huge literature about learning both arithmetic and Boolean circuits. In fact, many of these results came from this conference. But the sad story is, many of these results, if you tweak them a little bit, then, the answer is unknown. So we do not know how to learn even slight generalization of this, and this is very sad. And one natural question, of course, that may rise here when you see this is, why can't we learn everything? I mean, we wish we could learn everything, why can't we do it? And there were several explanations trying to answer this very important question. One of them relates to cryptography, saying, well, we cannot learn everything. Why? Because if we could learn everything, we could learn some cryptographic primitives and break them. And we do believe in the security of cryptography, so it seems unlikely we can learn everything. Other type of explanations come from complexity theory, tying learning to some complexity theoretic assumptions like NP hardness and others. So actually we have an interesting talk about this coming forward, so I'm not going to talk about complexity anymore. What I'm going to talk about now is circuit lower bounds. So what are circuit lower bounds is the goal of finding a function that requires large circuits. Now, if this is all I want, this is actually an easy task. Why? Because a random function will do the job. It's easy to show that a random function will have exponential circuit complexity with high probability. So this wouldn't be interesting. To make it interesting, what we want is an explicit function. We want the function to be able to describe it in some explicit way. It turns out that once we insist on being explicit, then the reality becomes very, very bad and very, very sad. We have only very, very big explicit lower bounds, linear and quadratic, both arithmetic and Boolean. And it's even, to make it even more sad, what we're looking for here is a haste in a haystack. Because there are many functions like this, we couldn't find even one. Why am I telling you about lower bounds? Because of the following interesting historical facts. If you go back to the previous slide and look at the list of the learning literature, you will notice the following interesting trend. Typically, a learning algorithm is preceded by a lower bound. So what happens is there is a lower bound, 1, 2, 3, 5 years later, there is a learning algorithm for the same class. Intuitively, why it happens? Well, usually, to prove a lower bound, you need to expose some internal structure of the circuit class, which later on leads to an efficient algorithm based on this structure. This is intuitively, of course, you want to ask the question whether it holds also formally. So this question was asked and answered by Fortman and Klivans et al. They show that indeed there is a formal connection here. That's what they show, that if a circuit class, a Boolean circuit class, is exactly learnable, then it automatically implies strong explicit lower bounds against this class. So it's formal connection. What's even more interesting is the recent result that shows that a reverse direction also holds. There is a result that was like, it will be on CCC, that shows that if you have a lower bound on a certain kind, then we can turn this lower bound into a learning algorithm and pack learning algorithm, which is, I think, very, very interesting. So learning and lower bounds have a lot in common. What is missing from this slide, so, is what can we say about arithmetic circuits? It's not on this slide, and this is exactly where we come in, and this is the main result of the paper. We show a similar statement for arithmetic circuits. So we show the following. For arithmetic circuit class, if an arithmetic circuit class is exactly learnable, then it implies exponential explicit lower bounds against this class. And to elaborate on this, we don't care what this exact algorithm is. We don't care if the hypothesis is an arithmetic circuit. It can be anything. In fact, the same thing holds with the previous result. There is this result uses the algorithm as a black box, so it doesn't have to be. However, if we make the specialization a requirement that we want some more, that we actually get other interesting results, specifically if we want to learn the class of general arithmetic circuits, and we require the algorithm to be proper, namely that the hypothesis be arithmetic circuits, then we get the fact that the following happens. If we can learn if there is an exact learning algorithm with membership and equivalence queries, then we actually don't need the equivalence queries. We can do with membership queries alone. This is quite interesting result, because we know in the Boolean, this is by far not the case. In Boolean, we have many examples of classes when if we do away with equivalence queries, then you have exponential requirement for number of queries. Now, like really fast, why it happens. So if you, the question is, well, let's try what people did for Boolean and do it for arithmetic, so it doesn't work. Why it wouldn't work? Because if we try to run what has done before, then it will might produce polynomials of high degree. So what's wrong with that is the fact that polynomials of high degree it's easy to show that even univariate polynomials of high degree require high circuit lower bounds, so it's not interesting. The interesting question is usually, let's find a low degree polynomial that requires high circuit complexity, and this is what we do. This is a more technical version of our result. For every circuit class, if we have an exponential, if we have a learning algorithm for the class, that we get a multilinear polynomial that requires exponential circuits. This is the more technical elaborate result. Just one word of how it works. If you think about polynomials as vectors, as a linear space, multilinear polynomials live in a slow dimensional vector subspace. So what we show is we ensure that the outcome of this algorithm, of the KKO, lives in a low dimensional vector space using linear algebra. So just to sum up, what we show that learning algorithms for arithmetic circuits should be challenging because it requires proving explicit strong lower bounds, something that we are light years away of proving, because explicit lower bounds, as I've said, I believe to be a holy grail of this line of research. We also have other results which I didn't have time to mention, and I'll be glad to discuss. And there will be more interesting, some open questions here, how you see a more direct connection between these results.